भाई सभी लोग चुप हो जाएं। तो today the topic we are covering is that can we write governing equation in generic form. What is a generic form? Converting your governing equation into generic form. Okay, I'll first slightly revise what we have done, basics, and then we will proceed to the article from where we have to start today. Okay. Now I told you that all these governing equations, so first basic thing you have to remember is that all these governing equations are basically conservation equations. Okay, and they are we know that they are conservation of mass, momentum and energy equation. This is what we know. Now if we talk about momentum equation, these conservation equation, we can see that this is our control volume, right? And there are 4 terms in this, and all of these 4 terms balance each other. Together they form sum equal to 0, and that is why they are called conservation equation. The first term is accumulation term, that is any physical quantity, how much of that is collected within the control volume. Now then you have advection term, which tells you that a physical quantity which is flowing out of the control volume along with the fluid. Okay. So if a parcel of mass is flowing out, it is carrying with it mass, momentum as well as energy. So whenever mass moves out, all these 3 things also go out. So that is advection. It can also come in. When the mass enters in the control volume, you have mass entering in, you have momentum entering in, and you have energy entering in the system. Then you have another term which is a diffusion term. Diffusion term is basically flow of a physical quantity without mass flowing in or out. Okay. And it is possible through the gradient. Suppose there is a temperature gradient, heat can flow in and flow out. There is a pressure gradient, then the momentum can flow in or flow out. Shear forces, momentum can flow in or flow out. Okay, and of course because no fluid is flowing in, so your mass is not flowing in or out. But when you have species, you can talk in terms of concentration of a particular species, and because of gradient difference, it can enter in and it can come out. And the 4th term is the source term, that is the same physical quantity being generated within the control volume. For an example, energy can be generated within by chemical reaction or electric current, right? Now when you put up all these quantities together, you find that accumulation plus advection is equal to diffusion plus source. This will always be true if you have any quantity which is physically conserved. Okay, and therefore all Navier-Stokes equations which you have, they contain 4 terms which can be grouped like accumulation, advection, diffusion and source term. Okay, Some terms may be there, may not be there, but all the terms will fall under this category, one of the or the other category. Okay. Now, to derive this whole scenario, we have already done this. I am just recapitulating what we have done before. We take up two quantities. One is phi and the second is psi. What is the relation between the two? That you can say phi is psi per unit volume. So it's a density of psi. That is the physical relation between the two. So if your phi is equal to that, okay, we have examples here. So if you have phi is equal to rho, you will have psi equal to mass, or in other words, psi by volume will be equal to phi. Similarly here, if psi is momentum, phi will be specific momentum per unit mass. Psi will be internal energy, MCVT. Phi will be specific internal energy. And sometimes we use this quantity also, psi as total energy and phi as specific total energy, where you add kinetic energy to thermal energy. Okay. So in a way, all these quantities, you can say, if they are specific, you can talk them as phi, and if they are total, you can talk to them as psi. Okay. So actually, if you write equation in phi and psi, you can write all the 5 equations together. Same formulation can express all the 5 equations, which is a helpful in a way that basically it is easier to write the program. So you have to write the same program for all the quantities. Only thing is that you keep on changing value of phi and psi. Okay. So this is we had talked about this already, accumulation term, and in accumulation term we get this. I'll come directly to this. We have done this derivation, del phi by del t is equal to 1 by volume of the control volume and del psi by del t. So you can say that del phi by del t is what? It is rate of psi accumulating in the control volume per unit volume of the control volume. Right? So this term represents what? Either you can write from the left side, interpret it from the left side, or you can interpret it from the right side. On the left side, it says the rate of change of a specific physical quantity. From the right side, you can say it is the accumulation of a physical quantity per unit time, per unit volume of the control volume. Okay, whichever makes better sense. And I think the right one makes the proper sense of physical sense of the thing. Okay. So for an example, if you write del rho by del t, it will come out to be accumulation of mass. So mass accumulating inside the control volume per unit time, per unit volume of the control volume. If your phi becomes rho v, this is momentum in, you can say y direction, because v is, one can write as v is vy, or any direction you can take. So rho v is the specific momentum. From the right side you can say the rate of momentum accumulating in the control volume per unit volume of the control volume. That you can find out. And same thing you can write about energy also. This is your specific internal energy. So you can say this term del rho CVT by del T is nothing but rate of internal energy accumulating in the control volume per unit volume of the control volume. This is how you can define. And up to this point we had done. I have just summarized what we did last time. Now we look at the term advection term. Even advection term we had seen. This one we have seen. And here we come to this conclusion that u phi del u phi by del x is equal to this term, and we can interpret it like this: q2 dot q2, this is the q2 dot is the volume of the fluid flowing out. Phi 2 is the specific value of the physical property. So when you multiply it by the volume, you get the physical quantity. So you can say that this term is giving you how much of a physical quantity flowing out per unit time, per unit specific volume, per unit volume of the control volume. And this is the term which is the entering in. Q1 dot is the amount of fluid entering in. Phi 1, when you multiply by phi 1, you will get psi 1. So what you will basically get that this is, so if you write this del u phi by del x, you will get that psi exiting from the right side, psi entering from the left side, the difference of the two. So this is equal to the rate of psi flowing out of the control volume in x direction per unit volume of the control volume. So this term is telling you how much of psi is flowing out per unit time, per unit volume of the control volume. Okay. Now this is in x direction. You can add up other also y and z direction. So what you get is this term, because if you add these three terms, this one and this one, what you will get is this. This is sum of these three. And here each we had three for this: phi x, psi y and psi z. So all these are put together. This tells you, so a particular quantity multiplied by velocity, this is a physical quantity, you multiply it by velocity, take the divergence, this will be equal to rate of psi flowing out of the control volume per unit control volume, per unit volume of the control volume. Okay. And okay, where your psi is again same as the phi multiplied by volume. So you can say they are, one is a specific quantity, the other is a total quantity, right? Psi is volume multiplied by phi, or phi is psi divided by volume. Specific. The easiest and most common example is mass and density. Mass will be equal to psi and your rho will be equal to phi. Okay, so this is how you interpret. Now, yeah, we were at this point last time. So example of advection. Now if you take phi as rho u, right? So what do you get? Psi as mu multiplied by volume, and this thing is telling you this is nothing but this, where psi is mass. Okay, so okay, yeah, this is your momentum in x direction per unit volume. So this will be psi mu will be equal to momentum in x direction flowing out of the control volume from all the surfaces. Now you have all the three components here, from all the surfaces along with mass, because this will flow out by mass only, per unit volume of the control volume. Okay, and if you write phi as rho e, so phi will be rho CVT and your psi will be equal to m CVT. Now if you write the equation, this equation, right, where left side you are multiplying a specific internal energy with velocity, finding its divergence. This is nothing but psi 2 dot minus psi 1 dot divided by delta VL, where psi is nothing but phi into delta VL. So this will be nothing but m CVT. So what it is telling us, how much of this is the internal energy, rate of the internal energy or thermal energy flowing out of the control volume from all the surfaces, three ends put together, along with mass, because it will be going with mass, per unit volume of the control volume. Right. Remember that this divergence term gives you how much is flowing out, and diffusion term gives you how much of it flowing in. Of course, you can put negative sign on both of them and the flow would reverse. So if you put minus on the diffusion term, it will be thing flowing in, flowing out. Okay, that. Now we come to diffusion term, and we will do this in detail because we were at this point. So first we will write like this. This is the diffusion, this is how it is written, diffusion term, where this gamma is a diffusion coefficient, general term, diffusion coefficient. This is the gradient of the parameter on which the diffusion depends. It could be temperature gradient leading to energy flow. It could be concentration gradient leading to mass flow or a particular species flow, or could be other things also. Okay. And shear force, which is shear force is nothing but gradient of velocity. So the gradient of velocity is actually giving you shear force, which is actually giving you transfer of momentum. Okay. Now on the right side is the quantity psi x dot per unit area. Now here your psi is again equal to phi delta VL, and this we will prove later. At the moment you take it like this. From here, this equation you cannot say that unless until you know what is gamma, you cannot say that psi is actually equal to phi delta VL. This thing comes when gamma is written in the units of meter square per second. Okay. So that we have to modify the equation, write gamma in units of meter square per second, then you will get this thing. Okay. And then we can do it. That thing is possible. So what we are doing here is we are assuming that this is the equation. This is the diffusion equation. Now this gamma del phi by del x is interpreted as a physical quantity psi flowing back per unit time and per unit area in x direction. Because this gradient is in x direction, the flow will be in x direction, and because in the gradient on the right side the gradient is higher, the value is higher of phi, and that is why del phi by del x is positive. If this is positive, del phi by del x is positive. Now if you say that del phi by del x is positive, this means phi 2 is greater than phi 1, which means the right side value of phi is greater than left side, which means from the right side the flow will take place in the left side. Okay, because it's gradient dependent, things will flow from the higher value to the lower. Okay, so this is telling you that's a physical quantity psi flowing back per unit time, per unit area in x direction. Okay, area also comes in here. Okay, yes, if you are confused here, you can take it like this. If you have T1 here, T2 here, such that T2 is greater than T1, then the heat will flow like this. So if del T by del X is positive, then your Q flow is in negative direction. Okay, and that is why I am saying it is flowing back in x direction. Now, so if we first calculate this quantity, we are finding the derivative of this again. So far we were talking about this term, now we are talking the derivative of this. So this derivative can be written as value of this on the right side, value of this on the left side, divided by delta x, where delta x approaches to 0. Okay. Now, so this thing can be written like this. I can multiply upside numerator by del y by del z and divide by delta y by del z. No harm. This algebraic equation we can do it. So then it is your something like this. Now this term is on the left side, it is there, and this is, so something is flowing in from the right side, something is flowing out from the left side. Okay, and you write it like this. Now we are introducing a term psi here, the same which we have talked about. So this is equal to psi x dot. Still we have not proved that psi is volume multiplied by phi. That we will do in the end. Okay. Okay. So what does it mean? We have already talked about it. This is the assumptions we have taken. This is the assumptions we are taking. So we say that this term is nothing but physical quantity psi flowing back in x direction across the surface del y by del z per unit time. Okay. And okay, you can divide it by delta y. You can divide both sides by ये जो क्वांटिटी है ना, ये वाला, इसमें del y by del z यहाँ पर है, तो ये phi 2 dot x and phi 1 dot x बन गया. So it is telling you that is the quantity flowing back in x direction, right, per unit volume of the control volume. Okay. Now you can look at like this. This term will be equal to psi xx dot, and this term is equal to psi x dot. So now there will be difference between these two terms because everything is changing with space and time. So these will not be same, and that is how net quantity is flowing in. Okay. So so similarly you will find that this term, what it is telling you, how much of psi is flowing in from the y direction into the volume per unit volume of the control volume. Similarly, this is telling you how much of psi is flowing in to the control volume y direction, and this is telling you about the z direction. If you add these, the term, three terms, you get term like this. You are adding these three terms for z, for y, and for x, and these three terms when you add up, it will become equal to this. This is what we are adding on the right side. Okay, and you know that we have already done that this term is equal to this, this is equal to this, and this is equal to this. Okay, so what does it become? This term will become, this is psi, sum of all the psi's flowing in x direction, y direction, and z direction. Okay, so the net psi flowing into the control volume per unit volume of the control volume per unit time. Okay, so psi 2 is a rate of psi flowing into the control volume from all the surfaces by diffusion. Psi 1 is the rate of flowing out from all the surfaces by diffusion, and this gives you the difference. Okay, so this term is basically giving you psi 2 minus psi 1 dot per unit, the rate of psi flowing into the control volume by diffusion from all the surfaces per unit volume of the control volume. So if your equation is of this form, still we have not transferred into physical form, physical quantities. Okay, we have talked in terms of phi and psi, but what are phi and psi we have not talked about here, at least in case of diffusion. For accumulation, we have given the three examples. What is phi and psi? One was for mass, one was for momentum, one was for energy. Then we came to advection. Again we derived the equation in terms of phi and psi, but then we said phi can be, you can say your mass, it can be phi can be density, specific mass, phi can be specific momentum, phi can be specific energy. and on the other side psi can be mass, momentum and energy, total energy. Okay, so now when we are talking about diffusion term, we are still at phi and psi. We have not substituted them with the physical quantities. Okay, but before that, what we do, we are deriving this relation between psi and phi. Remember, I told you that psi is equal to phi into delta VL. Is it really so? Let us see. So this was the equation where we started from. Okay. Now, so this term is represented as or interpreted as a physical quantity psi flowing per unit area, right, per unit time in x direction. Okay, and if you and if you are talking in terms of this, so you can talk this term with area, without area. Okay, so on one side, if you are talking with area, it is talking about psi without area. When here you are talking without area, so it is per unit area. Same thing, you have only moved area from the left side to the right side. Okay, so if you are talking about this term, it can be interpreted as physical quantity flowing back in x direction across surface delta y delta z per unit time. Okay, now you see that this, if you put the units, you talk in terms of units. So this will be units of, this is gamma, we will put the units of gamma here. This is phi, we will put the units of phi here when the need is. This will be delta x is, del x is meter. On the right side it is psi, we will put the unit of psi. Area is meter square and psi dot is second. So what we have, partially we have converted, used the units. For x we have put meter, for area we have put meter square, for time we have put second. Okay, now if you put gamma is equal to meter square per second, area per unit time, right, then what you will get, balancing this, you will get phi this. So actually you will define gamma in terms of meter square per second, right? Then what will happen? Your psi will be equal to phi delta L, so delta volume, or you can say phi will be equal to psi per unit delta volume. If your gamma is of the unit of meter square per second. Okay. So normally we write gamma, we make gamma, whatever you will find, we will do it as an example. We will, for a heat conduction equation, we will show that unit of K is not meter square per second. What are the units of K? Joule per meter per second, something like that, right? वो एरिया भी आता है उसमें, वो सब चीज़ें आके, we'll see that. Okay, so if gamma is written like meter square per second, then psi and phi will be volume. Okay, so what we will be doing, we will be modifying our gamma in such a case that psi and phi will be related as specific and the total. So it will help us understand the thing. Okay. So now what we do, we take this equation. This is the equation for conduction. Fourier's equation of conduction of heat. Now remember that conduction is basically diffusion of energy. Convection of heat is advection. Where the heat flows along with the flow of fluid. But here in conduction, there is no flow of the mass, no flow of the fluid. Even if two fluids are there, conduction we talk in terms of solid, but conduction can take place in liquids also. Right? You keep two liquids, right, and they are non-miscible. One is hot and one is cold, right? The heat flow will be through conduction without the flow of movement of the, because the density difference is such that they will not allow the fluid to mix. So it's possible even for the fluid. So there is a conduction in air, right? You can look at the conductivity of water, conductivity of air, right? Which means that air or water is at a, they are not whirling or they are not mixing, they are just stationary at a molecular level, or at least at a particle level, I may say. Molecular level, there is always a movement. So even liquid, the heat transfer may take place. Suppose you heat the liquid from the top, the bottom gets heated up by conduction, not by convection. If you heat the liquid from the bottom, the top will get heated up by convection along with conduction, but majority will be convection. But if you are heating it from the top, there will be no convection, it will only be conduction, right? So why I am saying this is because you should not think that conduction will take place only in case of solids. Okay. So conduction in the fluid dynamics is taking place at the boundary, where the one boundary is solid and the fluid is flowing along it. So at the boundary, conduction is taking place. And also conduction otherwise also in the fluid takes place. But when we talk about solid, there is no convection, so we can easily see that it's all conduction. So this is a diffusion equation, and this is how we write. Now it is familiar to you that this is thermal conductivity, rate of change of temperature in x direction will give you the amount of heat flow. So this tells you, this equation is telling you that the temperature on the right side, temperature on the left side, temperature on the right side is higher. That means the heat will flow in x direction, in the backward direction, and the heat flow will be equal to K conductivity multiplied by del T by del X into area. Okay. Now, so the total heat flow will be when you multiply by area, and so you have you can talk in terms of total heat flow, or you can talk heat flux per unit area of heat flow. So this is telling you what heat flowing Okay, per unit time, per unit time through the two opposite surfaces del y by del z of a cuboid into a cubed will be like this. तो इसको आप इस तरह से लिख सकते हैं, राइट से एंटर कर रहा है हीट और लेफ्ट से निकल रही है हीट, एंड दिस इज ऑल इन एक्स डायरेक्शन ओनली. Will add up other direction and it will become from any direction. Okay, now and you see this is the heat flow in from the right direction, this is the heat flow out from the left surface. The difference is this. So this is how you get this equation. Okay? And so your equation is of this form. If you want to find out, so this, if you use this equation and divide by volume, you get this equation. So what is this? Amount of heat flowing in the x direction per unit volume of the control volume of the cuboid. Okay. Similarly for y direction, this is for z direction. You add all the three, you will get this total heat flow. So it is net heat flow into the cuboid per unit time and per unit volume of the control volume. Okay? And this is the equation. Is the same equation which we have written like gamma and gradient of T. Okay? You have a gradient, you multiply it by some coefficient, then you take the divergence. Okay? Square terms आ जाती है इसमें, differential you get the square terms. Now what you do, in this equation you multiply rho CV on this side and rho CV on this side. Actually you cannot do it because in a fluid rho is changing, so you cannot, these two are not same, these rho CV and this rho CV are not same. Inside the derivative and outside the derivative you can't multiply. CV is okay, CV is constant, so you can keep it outside as well as inside. But just to tell you what physically it means, right? You can make it multiply both sides. Okay. So what it will become? This will become your equation. This will be your gamma, and this will be your phi. Okay. Now you see that phi is rho CVT. What is it? Internal energy per unit volume multiplied by gamma, it will give you energy flowing in, okay, per unit control volume, per unit time. Okay, so this is the equation similar to psi dot is equal to gamma, divergence of gamma. These are similar equations. But when we use this equation, the units of this was meter square per second. And then that is why we said that this psi is equal to phi into delta VL. Now you see here that, okay, we are finding the relation between Q and T, and you will find that, okay, this equation you are familiar with, okay, this we use as it is. Now if you take this equation as this. You write this as psi dot per unit area. You can write it as qx dot per unit area. Same thing, right? So your phi is equal to rho CVT, right? And now you see that rho CVT into delta VL will be equal to m CVT, it will be psi, it will be equal to q. And so you have this psi is q, psi is equal to q, q is equal to delta VL, phi VL, and this is equal to nothing but rho CVT delta V. So in a way you can write like this. So these are the terms you are using. So here if you write equation in terms of phi and psi, your psi becomes q, which you are familiar with, and phi becomes this rho CVT, right? And now you see that what are the units of gamma. We know that gamma of, now this relation will be true only when gamma is meter square per second. So what we had done is, okay, this is, we know, we had done this. So in our case gamma was kT by rho CV. You check the units of this is meter square per second. Right. So in case of your conductivity, if you are writing equation in terms of gamma, psi and phi, okay, we are just telling you that gamma is nothing but k by rho CV, okay, psi is equal to q, and phi is equal to, or you can say m CVT, and phi is equal to rho CVT. This is what it is telling. They are all interrelated. But why we are writing in terms of phi and psi then? Because when there will be some other quantity, diffusion, right, then the same equation can be written for that also. Where it will occur? It will occur diffusion of momentum. Diffusion of momentum means you are doing nothing but the momentum is going in. No mass is flowing in, but the momentum is going in. You see, if you have this block here, I can apply force, nothing has entered the control volume, but momentum has gone in. This is diffusion, right? So the shear forces basically give you diffusion, okay? Diffusion of momentum. Now, then we have source term, okay, and source term is written just like that, rate of generation of psi in the control volume per unit volume of the control volume, and written as S phi. Now we have described all the four terms: accumulation, advection, diffusion and source. Now we will see the equations there of the governing equation, and we'll see which term is talking about what. So come back to this. We started from this accumulation, advection, diffusion and source term. Okay. So whichever equation you will pick up, conservation equation, all these four terms will be there, or they will be able to categorize them in that. It may not be or may not be there. Either they are there or they are falling in one of these. Okay. So you take this equation, these are your basically this is your generalized equation of conservation. Okay, this is the first term. We are talking in terms of phi. This is the accumulation term, this is the advection term, this is the diffusion term, and this is the source term, and this is the general equation. All equations can be put like this. Only thing what will happen, phi and psi will change. Okay, so now if you have your continuity equation here, this is your continuity equation, this is your accumulation term, this is your advection term. Diffusion term is absent, source term is absent, because mass cannot be generated within the control volume and it cannot be diffused in. If the same equation was in terms of species, here we are talking phi in terms of mass, there is only one species. If there are multiple species, then you will talk in terms of rho 1 or rho 2 and rho 3 and so on. Then the diffusion term will be there, right? And the gradient will be the change in density, the concentration. Okay? But here, if there is only one mass, it will be like this. Okay? Then you take, this is your momentum equation. This is your accumulation term, this is your advection term, right? And this is your diffusion term, double derivative. These terms are nothing but del u by del x, right? And the remaining term are put in source term. So what we do, whatever the terms are there, either they are in three categories, the remaining is put in the fourth source. Okay, and this is also when we talked about aerodynamics, we have used that Stokes relation, and we converted this tau xx, tau yy, xy and tau xz. Now you can see that they are double derivative. They are basically diffusion terms. Okay, and you can see that here, without flowing in the mass, momentum is entering in, because there is a shear force. Okay, when you apply shear force, the body moves, nothing goes in. There is a diffusion. Okay? And these terms are, and when you talk about energy equation, this is your accumulation term, this is your advection term, okay, this is your diffusion term, thermal energy, and all these remaining are your source term. So this is how you put them. Okay, so you can interpret whenever you are getting an equation that what is happening there in the conservation, because only these four things can happen. Either there will be some accumulation somewhere, or a source there, or something is flowing in, or something is diffusing in, right? And you can interpret what is physically happening in this equation, which term is responsible for what. Okay, so this is what the generalized coordinates are. We will stop here. Okay, this is again the extension of that same thing, total energy equation. You can find yourself again accumulation term, advection term, diffusion term and source term. Okay, so